So, and the Jacobian determinant. So the quote unquote new function, y1 equals x1, if we're differentiating that with respect to x1, x2, x3, the only meaningful one that we would get out of that would be the x1 derivative, which would be a 1. Everything else would go to 0. Right? For y2, the only meaningful one would be the x3 derivative. Everything else would go to 0. But then for y3, the derivative, when you take the derivative with respect to x1, it would go to 0. But when you take the derivative with respect to x2, you're going to get 8x2, 8x of 2 to the first power. And then when you take the derivative with respect to negative 2x of 3, you'll get the negative 2. All right. So what we would be looking for in this Jacobian is the determinant of this 3x3 square matrix. All right. Now, there is some strategies that you can use to make your life a little bit easier. One of those strategies is, and this is kind of diving a little bit into the world of linear algebra. I mean, we talked about this before in the sense that, sometimes it's not always necessary to do, but you are allowed to swap rows in a matrix. And the reason why you're allowed to do that, so if you were to say, for example, like you were solving the equation x, the system of equations, I should say, x plus y equals 1, x minus y equals 1, something very basic, right? If you were solving that system, who cares if you write it like this or if you write it the other way around, right? So it's the same system. All right. So same system would yield the same solutions. All right. So you're allowed to swap rows. All right. And again, that's something that, if you have experience with linear algebra, you know that already. It's a very basic rule. It's called an elementary row operation. The emphasis on the elementary. Right. So what I could do is rewrite this as 1, 0, 0, 0, 8x of 2, negative 2, and then 0, 0, 5. All right. The benefit of writing it that way is that what I've created is a triangular matrix. This is upper triangular. Right. So if you use, we talked about this as the case where you use the main diagonal as a line of demarcation. If either side of that diagonal contains only zeros, then it's a triangular matrix. If both sides contain only zeros, then it's what we call a diagonal matrix or diagonalized matrix. Right? In either event, in order to figure out the determinant, all you'd have to do is multiply down the main diagonal. All right. So that's so you can avoid the cofactor expansion. All right. So the Jacobian would be 1 times 8x of 2 times 5, which would be 40x of 2. All right. Now, the Jacobian is always going to be, well, any kind of determinant is always going to be, at least when it's in the context of area, it's always going to be an absolute. All right. So whether you at least keep it in mind that this is an absolute value, or you chuck an absolute value set of brackets around it, either way is fine, as long as you have it in your mind that you're only looking for positive numbers here. Right. What a lot of people will do is they'll throw the absolutes around it just because they're worried that they might forget. when, when and if they actually know the value of x of 2, they plug it in and they report a negative value, then they start kicking themselves. It's like, oh, I knew it was supposed to be non-negative. Why did I leave the negative? So just something to keep in mind, right? If you wanted to do it with cofactor expansion, you totally could. It would give you the same value. I believe, if I'm not mistaken, when I did it with cofactor, I want to say I did it across the first row, and I ended up with a negative 40 x of 2. But I'm just doing it in my head right now. It's definitely negative 40 x of 2 if you do it across the first row, in which case you drop the negative anyway. All right. So, or you leave the negative and throw some absolutes around. Either way. So that's a little modification of an example, just so you can see how some nifty linear algebra concepts could come into play and be somewhat helpful. I always feel bad kind of throwing that stuff out on you or at you on the fly. I kind of equate it to an old TV show that I used to kind of watch. I didn't really watch it. My brother watched it, but I watched some parts of it. Dragon Ball Z and Yu-Gi-Oh. Those kind of shows. The Yu-Gi-Oh in particular, it's like it always seemed like like you're playing. It's cards, so it's like I have a card where you're going to go to the demon dimension. Well, I have a card that's going to save me from the demon dimension. And I gotta. It's like magic. You got these cards that come out of nowhere. It's like if you were playing poker with somebody, and like they had like the best possible hand that you could have, and then all of a sudden you were able to like invent a new hand that is somehow beats the best hand in poker. Like that. Sometimes it feels like when I'm introducing the linear algebra concepts that it seems like I'm doing that. Like, oh, by the way, here's a rule that'll do the job for you that I swear I didn't just make up on the spot. But they are legitimate rules from linear algebra. You get more experience with that course, you realize that it is true. Like being allowed to swap rows. Seems like it came out of nowhere, but it was very helpful. Right. And it's true. It's true. So that's the new page 91. Right. So